Hi, Bobcats. This week starts our study of gases, which is Chapter 7 in our textbook, the Sapling Learning IGC. Our objectives for this video are to look at the particle picture for solids, liquids, and gases and compare and contrast the three states of matter, and then also look at the standard variables or parameters that are used to characterize gases, and also to define something that pops up over and over again in problems, which is STP. So when you see that, you'll know what that means. When we compare the three states of matter, solids, liquids, and gases, in terms of what their particles are doing, the three states do something very, very different, although there are some similarities. So for instance, if we start talking about the solid phase, in a solid, all of the particles have a particular spot where they're assigned to be, and while they move a little bit around those spaces, they generally stay very, very close to those assigned positions. If we compare that with a liquid, the particles are also very close to one another in a liquid, but now they're free to move around a little bit. To give you an analogy for these two states of matter, a solid would be like how students are sitting in desks during a normal lecture class. And then the liquid is what happens as soon as the instructor dismisses the class and everybody stands up and starts moving around. They're still close, but they are all moving. And just like in the solid phase, when students are seated in their chairs, nobody is absolutely frozen in position. Everybody's moving a little bit. You might be writing, taking notes. You might be getting an eraser out of your backpack. But everybody has a particular position to be in. Gases, on the other hand, are much more disorganized. The particles are moving all over the place and they're separated by really big distances. To see an animated version of this, these cartoons here, if you go to Sapling Learning and then you click on the image of the textbook over on the far right side, go in the textbook to section 7.1 and look at figure 7.1 and play this little video, and you'll see an illustration of the particle, or an animation of the particle motion. The first of the parameters that are used to characterize gases that I want to delve into is pressure. It'll be abbreviated with a capital P. And if you've taken a physics class, you may have seen a definition of pressure as being the force divided by the area over which that force is acting. So when we're talking about gases, the force is exerted by the gas particles colliding with the walls of their container, and the area is that surface area of the container. There are a whole lot of units that are used to measure pressure. The ones that are most common that we will be using are atmosphere, millimeters of mercury, and torr. Pressure is measured experimentally with something like this apparatus over here on the right, which is known as a barometer. In this arrangement, there's a pool of mercury down at the bottom, and that mercury extends up into an inverted glass tube. The height of the mercury inside of that tube above the pool is a measurement of the pressure that's exerted by the air that's pushing on that pool of mercury. And so the simplest, most natural unit to measure pressure in is literally just measuring the height of that column. So if you watch a news broadcast of the weather, they'll say that our pressure is 30 inches of mercury, something like that. And it means they're using a tool like this, and the height of that column of mercury is 30 inches. Well, being scientists, we don't usually use inches, we use the metric system. And so at normal atmospheric pressure, what is experienced at sea level on a clear sunny day, the height of that column is about 760 millimeters. So the unit that we would use there would be 760 millimeters of mercury. Now, chemists also, or scientists in general, like to name things after people. And so this unit got renamed as TOR after an Italian scientist, Evangelista Torricelli, who did a lot of experiments with gases and pressures. And so that column that's 760 millimeters tall is equivalent to 760 torr. It's like saying dollar and buck. Torr and millimeters of mercury are the same thing. And then to make some calculations a little bit easier, 1 atmosphere was defined to be the same amount, so that for things that are happening at normal atmospheric pressure, we're just multiplying and or dividing by 1 when we do those calculations. The other parameters or variables that are used to characterize gases are temperature, volume, the amount of the gas, and pressure. Well, we already looked at pressure. So temperature, whenever we are doing gas law calculations, has to be in terms of Kelvin. Typical thermometers will measure in terms of Celsius. So right here's that equation to convert. So if you're given a temperature in Celsius, you're going to add 273.15 to it in order to get that temperature in Kelvin. And always, always, always use Kelvin if we're doing gas law calculations. Volume, I think we've already done volume quite a bit this semester. So the one thing I just wanted to refresh you all on is that 1 liter is equivalent to 1,000 milliliters. So if you're given a volume in milliliters, you need to move the decimal 3 places to the left to convert that to liters. For the amount of gas, well, in the lab, we'll most commonly measure that amount in terms of grams. So in order to get it into moles, which is what the ideal gas law calls for, you're going to have to use a radiation sign conversion. 1 mole is equivalent to the molar mass in grams. So basically, if you're given the amount in grams and you need moles, you're going to divide the given amount by the molar mass. And then last but not least, pressure. In some of our gas laws, you have to use atmospheres, and in others, it doesn't matter as long as you use the same units on both sides of the equation. In some problems, instead of giving you a temperature and pressure, the problem will just say this gas is at STP. Well, STP stands for standard temperature and pressure. There's the S. Here's the T, and here's the P. So that's where STP comes from. And standard temperature and pressure is defined as 0 degrees Celsius, which would be equivalent to 273 Kelvin, and 1 atmosphere of pressure, which would also be equivalent to 760 millimeters of mercury. If you think back to when we did our mole conversions and we were using the radiation sign, we said that 1 mole of a gas was equivalent to a volume of 22.4 liters. And there's a qualifier on that, that's at STP. So this number is only, we can only use this number if we are at STP. If we're at a different temperature or we are at a different pressure, that 22.4 liter value is not valid. And so we'll have to use a different gas law to figure out what the volume is. So here we are back to the objectives for this video. Take a close look at each one of these objectives and make sure that you can do each one of these things without referring to any extra reference material. If you can, great, you're in great shape for this first video. Eat 'em up, cats.